The morning air over Recklinlaz was cold enough to make breath visible, even at ground level. It was April 24th, 1945, and Hauptmann Hans Fay stood beneath an aircraft that shouldn't exist, not here, not now, not in the hands of the Luftwaffe. The Boeing B-29 Superfortress towered above him, its polished aluminum skin reflecting the weak German sun. American star insignias had been hastily painted over. Crude swastikas marked the tail, but the machine itself was untouched, intact, and impossible. Fay had flown 327 combat missions. He had survived attacks against British Lancasters, American B-17 seconds, and the massive Soviet P-8 seconds. He understood the mathematics of interception, the closing speeds, the deflection angles, the brief windows where an attacking fighter could fire and escape before defensive guns found their mark. He had mastered these calculations so thoroughly that they had become instinct. But standing beneath this bomber, reading the technical specifications that German intelligence had compiled, he felt something he hadn't experienced since his first solo flight: uncertainty. The specifications claimed this aircraft operated routinely at 30,000 feet. It cruised at speeds exceeding 200 miles per hour at altitudes where most German fighters could barely maintain level flight. That its defensive armament, 1250 caliber machine guns, was controlled not by individual gunners straining to track targets through manual sights, but by an integrated fire control system using analog computers to calculate lead and deflection automatically. On paper, these claims seemed exaggerated, American propaganda perhaps, but Fay had learned, through 5 years of war, that intelligence reports had a way of understating dangers rather than overstating them. And this bomber was here, physical and real, because someone in the chaos of Germany's collapse had decided that understanding it mattered more than pride. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within 3 days, Fay would climb into the cockpit of a Focke-Wulf 190 and attempt to intercept this aircraft using standard Luftwaffe doctrine. Within 3 days, he would discover why Japanese fighter pilots who engaged B-29 seconds over Tokyo were dying at rates that made no tactical sense. Within 3 days, he would understand that everything the Luftwaffe had learned about bomber interception had become obsolete the moment the first Superfortress lifted off from a runway in Kansas. But that understanding would come too late to matter. To comprehend what Hans Fay was about to experience, we must return to the summer of 1944, when German intelligence officers began receiving reports from the Pacific that contradicted every established principle of aerial warfare. The reports came through multiple channels decoded Japanese communications, interrogations of downed Allied aircrews, and eventually detailed technical assessments from Japanese engineers who had examined wreckage. They all described the same phenomenon: a new American bomber that operated at altitudes and speeds that rendered conventional interception doctrine ineffective. The first confirmed encounter occurred on June 15, 1944, when B-29 seconds from the 20th Bomber Command struck the Imperial Iron and Steel Works at Yawata, Japan. Japanese Army Air Force fighters scrambled to intercept. Of the 75 B-29 seconds that participated in the raid, only 7 sustained serious damage, but 15 Japanese fighters were lost. The exchange ratio, the number of defending fighters destroyed versus attacking bombers, was catastrophic. Subsequent raids followed the same pattern. On August 20, 1944, during attacks on the Showa Steel Works in Manchuria, Japanese, pilots reported that their Nakajima Ki-44 fighters, capable interceptors at medium altitudes, struggled to reach the B-29 seconds operating height. Those that did arrive found themselves gasping for oxygen, their engines starved of air, while the American bombers cruised serenely above them, seemingly unaffected by the thin atmosphere. By November 24, 1944, when the first B-29 seconds struck Tokyo itself, the pattern was undeniable. The Japanese Fighter Command reported that standard interception tactics, the same tactics that had worked against B-17 seconds and B-24 seconds in China, were failing. Pilots who pressed attacks home were being shot down at 3 times the expected rate. Those who survived spoke of defensive fire that seemed to anticipate their movements, of gun turrets that tracked with mechanical precision, of no safe approach angle. German military attachés in Tokyo forwarded these reports to Berlin with annotations expressing skepticism. The Luftwaffe had spent 4 years perfecting the art of bomber interception over Europe. They had developed tactics that could crack even the most heavily defended B-17 formations. They had learned to exploit blind spots, to coordinate attacks from multiple vectors, to use cannon fire from beyond machine gun range. How could one bomber, regardless of its capabilities, render all of this expertise useless? The answer arrived at Rechlin in pieces throughout the winter of 1944 and spring of 1945. First came technical drawings, smuggled through intelligence networks that remain classified even today. Then came fragments of the fire control system, salvaged from a B-29 that had crashed in Manchuria. Finally, in late March 1945, came detailed specifications of the General Electric Central Fire Control System, the technological heart of the B-29's defensive capability. German engineers who examined these materials understood immediately that they were looking at something fundamentally different. This was not an incremental improvement, it was a paradigm shift. The B-29 Superfortress was born from a specification that most aircraft manufacturers considered impossible. In January 1940, nearly 2 years before the United States entered World War II, the Army Air Corps issued a requirement for a bomber that could carry a bomb load of 2,000 pounds over a range of 5,000 miles, at speeds exceeding 400 miles per hour. The requirement was absurd. The best bomber in American service at the time, the B-17, could carry 4,000 pounds, approximately 2,000 miles, at speeds barely exceeding 200 miles per hour. What the Air Corps wanted was an aircraft that could fly more than twice as far, nearly twice as fast, while operating at altitudes where existing bombers couldn't function. Boeing's response was designated Model 345. The aircraft that emerged from this design process would be the most expensive weapons development program of World War II, costing more than the Manhattan Project. It would require the construction of entirely new factories, the development of new manufacturing techniques, and the training of tens of thousands of workers in assembly processes that had never been attempted. The centerpiece of this development was the defensive armament system. Boeing engineers understood that an aircraft operating at 30,000 feet, beyond the effective ceiling of most contemporary fighters, still needed to defend itself during climb, descent, and from the handful of interceptors that could reach those altitudes. But traditional defensive arrangements, individual gunners manually aiming weapons, were inadequate. At 30,000 feet, the air temperature drops to -40 degrees Fahrenheit. The atmospheric pressure is 1/3 of sea level. Gunners in unpressurized positions would be unable to function. Even in pressurized compartments, the physical act of manually tracking a fighter moving at closing speeds of 400 miles per hour or more, while accounting for deflection angles and range estimation, pushed human capability beyond reliable limits. The solution was the Central Fire Control System. Developed by General Electric beginning in 1941, it represented the most sophisticated integration of mechanical computation, hydraulic actuators, and remote control ever installed in an aircraft. The system worked as follows. 5 gunner stations were positioned throughout the aircraft nose, dorsal, 2 waist positions, and tail. But instead of manually operating guns at their stations, gunners controlled remotely located turrets through computed sighting stations. When a gunner acquired a target through his sight, the system calculated the target's range using optical range finding. It measured the B-29's altitude, airspeed, and outside air temperature. It factored in the ballistic characteristics of .50 caliber ammunition. And it computed the precise lead angle and elevation needed to place bullets where the target would be, not where it appeared to be. This calculation happened continuously, 30 times per second, using analog computers built from gears, cams, and electrical relays. The computed firing solution was transmitted to electric motors that traversed and elevated the gun turrets. A single gunner could control multiple turrets. Multiple gunners could train their sights on a single target, and the system would automatically assign the turret with the best firing angle. The result was a defensive weapons system that eliminated the three primary limitations of human gunners: reaction time, calculation error, and physical fatigue. German engineers who examined the technical specifications understood the implications immediately. In a report dated March 19, 1945, an engineer at the Rechlin test facility, whose name remains redacted, wrote, "The American system does not improve human gunnery. It replaces it. The defending aircraft becomes, in effect, an automated weapons platform with human operators serving only to designate targets. The tactical advantage this provides is difficult to overstate. But understanding a system on paper and experiencing it in combat are entirely different things. The specific chain of events that brought a complete, functional B-29 to German territory in April 1945 remains partially classified. What is documented is that on July 29, 1944, a B-29 named Ramp Tramp, operating from bases in China, experienced mechanical difficulties during a raid on the Showa Steel Works in Anshan, Manchuria. Rather than risk ditching in Japanese-controlled territory, the pilot diverted to Vladivostok and made an emergency landing in Soviet territory. The Soviet Union, though at war with Germany, maintained official neutrality with Japan until August 1945. Under international law, the aircraft and crew were interned. The crew was eventually repatriated through Iran. The aircraft remained in Soviet hands. What happened next represents one of the most significant technology transfers of the war. Soviet engineers dismantled the Ramp Tramp completely. They measured every component. They photographed every assembly. They reverse-engineered every system. And they used this information to create the Tupolev Tu-4, a nearly identical copy that would serve as the backbone of Soviet strategic bomber forces until the mid-1950s. But the Soviets, despite their thorough analysis, apparently shared information with German intelligence services during the brief period in early 1945, when both nations still maintained covert communication channels. Whether this was done as a gesture of continued cooperation, as part of an intelligence exchange, or through other means remains unclear. What is certain is that by March 1945, detailed technical information about the B-29 systems had reached Germany, and by April, a physical aircraft, not Ramp Tramp, but another B-29 acquired through channels that remain murky, sat on German soil. The most likely explanation, based on fragmentary records and post-war testimony, is that the Japanese captured a forced-down B-29 inches early 1945 and, recognizing that their own technical capacity was inadequate to fully evaluate the aircraft's advanced systems, arranged for German engineers to examine it. The aircraft would have been partially disassembled, shipped by submarine or surface vessel to German-occupied territory, and reassembled at Rechlin. This explanation accounts for the timing the aircraft arrived in April, just weeks before Germany's surrender, and explains why only a handful of test flights were conducted before the facility was evacuated. It also explains why the aircraft was destroyed before Soviet forces captured Rechlin. The Germans wanted neither the Soviets nor the advancing Americans to know that they had possessed a complete B-29. Regardless of how it arrived, by April 24, 1945, the bomber sat on the Rechlin tarmac, and Hauptmann Hans Fay had orders to evaluate its defensive capabilities using the only method that mattered: simulated combat. Hans Fay was not a typical test pilot. Most Luftwaffe test pilots at Rechlin were specialists engineers who flew, or pilots who understood engineering. Fay was a combat veteran who understood tactics. He had begun the war as a reconnaissance pilot, flying unescorted missions deep into enemy territory where survival depended on altitude, speed, and the ability to avoid engagement. He had transitioned to fighters in 1942 and quickly demonstrated an aptitude for bomber interception. By 1945, Fay had developed a reputation within the Luftwaffe as a pilot who could analyze why tactics worked or failed. He didn't just follow doctrine, he understood the principles behind it. When assigned to Rechlin in early 1945, ostensibly to test modifications to the Focke-Wulf 190, he was actually being positioned to answer a question that had been troubling Luftwaffe High Command for months. Why were Japanese pilots dying in such disproportionate numbers against B-29 seconds? On the morning of April 26th, 2 days after his initial inspection of the aircraft, Fay conducted his first familiarization flight in the B-29. German maintenance crews had serviced the aircraft using captured American manuals translated into German. They had fueled it with German aviation gasoline, which was slightly lower octane than the American fuel. The Wright R3000. 350 engines were designed to use, but functionally adequate. They had test-fired the defensive guns using German 50-caliber ammunition manufactured to American specifications. Everything worked. The engines ran smoothly. The pressurization system maintained cabin pressure to 8,000 feet, while the aircraft climbed to 30,000. The fire control system powered up without errors. German engineers who had spent weeks studying the aircraft had concluded that it was not only functional but in better mechanical condition than most Luftwaffe bombers still in service. Fay's familiarization flight lasted 1 hour and 40 minutes. He climbed to 32,000 feet higher than he had ever flown in a bomber and was struck by how stable the aircraft felt. At altitudes where German bombers wallowed and fought for control, the B-29 cruised as smoothly as a transport at 10,000 feet. The pressurization meant he could breathe normally. The visibility from the cockpit was excellent. The control responses were heavy but predictable. In his flight log, preserved at the Bundesarchiv, Fay wrote, "This aircraft operates at altitudes where it functionally cannot be intercepted by most fighters. Those fighters that can reach this altitude will be operating at the edge of their performance envelope, while the B-29 cruises comfortably. The altitude advantage alone represents a defensive capability equal to armor or speed. But altitude was only one component of the B-29's defensive system. The real test would come when Fay attempted to attack it. The test profile was developed by Fay in consultation with other Rechlin pilots and the facility's tactical analysis section. It would simulate standard Luftwaffe interception doctrine as developed through 5 years of combat against British and American heavy bombers. The B-29 would fly a straight course at 30,000 feet, maintaining a speed of 220 miles per hour. This was slightly below its maximum cruise speed, but representative of speeds used during actual bombing runs when precise navigation was required. The aircraft would be flown by a German crew trained on the B-29 systems. The defensive guns would be loaded with German tracer ammunition, visible rounds that would allow accurate assessment of fire patterns without live bullets that could damage the intercepting fighter. Fay would fly a Focke-Wulf 190D9, a late-war interceptor specifically designed for high-altitude combat. It was powered by a Junkers Jumo 213 engine with a 2-stage supercharger capable of producing 1,770 horsepower at altitude. In theory, it was one of the few German fighters that could operate effectively above 30,000 feet. The attack profile would follow established doctrine. Approach from the rear quarter at a 15-degree angle, slightly high. Close to 400 yards, the effective range of the 190's cannon and machine guns, fire a 2-second burst. Break away using the superior speed of the fighter to escape the bomber's defensive fire envelope. This tactic had been developed through hundreds of combat missions. It worked because it minimized exposure time to defensive fire, while allowing the attacking fighter to bring its weapons to bear on the bomber's most vulnerable areas: engines, fuel tanks, and control surfaces along the fuselage. Against B-17 seconds and B-24 seconds, this approach gave an experienced pilot approximately a 60 to 70% chance of causing serious damage with a single pass, and approximately a 15 to 20% chance of being hit seriously enough to force and withdrawal. The mathematics were acceptable. An interceptor that could make 3 or 4 attack runs before exhausting ammunition had good odds of destroying or crippling a heavy bomber. The first test flight was scheduled for the morning of April 27th. Weather conditions were optimal. Clear skies, light winds at altitude, visibility exceeding 20 miles. The B-29 took off first, requiring nearly all of Recklin's longest runway to get airborne even with a reduced fuel load. Faye followed 10 minutes later, using Focke-Wulf's superior climb rate to reach altitude before beginning his interception run. At 28,000 feet, Faye's engine began to struggle. This was expected. The Jumo 213, despite its advanced supercharger, was operating near its ceiling. Manifold pressure was dropping. Engine temperature was climbing. Control surfaces felt mushy as the thin air reduced their effectiveness. Faye adjusted his oxygen flow and scanned the sky above him. The B-29 passed overhead at 32,000 feet, its 4 engines leaving contrails that painted white lines across the pale sky. Faye was struck by how large it appeared even at this distance, longer than a B-17. Wider, its wings massive even from below. He pushed the throttle forward and began his climb to intercept altitude. At 30,000 feet, the Focke-Wulf was barely maintaining level flight. Faye's instruments showed he was operating at maximum continuous power. Any attempt at aggressive maneuvering at this altitude risked stalling. He would have a chance at an attack run. If he missed or if the B-29's defences forced him away, he would need to descend, build up speed, and attempt another climb, a process that would take 10 to 15 minutes and consume fuel he might not have. This, Faye realised, was the first lesson. The B-29's altitude forced interceptors to attack from a position of weakness. German fighters climbing to 30,000 feet arrived exhausted engines, straining, pilots hypoxic, aircraft at the edge of controllability. The bomber operated there as comfortably as if it were at 15,000 feet. Faye stabilized at 31,000 feet, slightly above and behind the B-29. He checked his armament. For this test, his guns were loaded, but he would not fire. The goal was to evaluate the B-29's defensive response, not to damage the only example Germany possessed. He adjusted his approach angle to the doctrinal 15 degrees off the bomber's tail and began his run. Range, 2,000 yards. The B-29 filled his gun sight. At this distance, Faye could see details the individual engine nacelles, the plexiglass blisters of the gun turret positions, the name stenciled on the fuselage that German maintenance crews hadn't bothered to paint over. The aircraft appeared utterly stable, its flight path perfectly straight. There was no evasive action. It simply cruised, as if unaware or unconcerned that a fighter was approaching from behind. Range, 1,500 yards. Faye maintained his approach angle and speed. In attacks against B-17 seconds, bomber gunners would typically open fire at around 1,000 yards early enough to disrupt the attacking fighter's aim, but not so early as to waste ammunition on low-probability shots. The B-29's guns remained silent. Faye wondered briefly if the defensive system was malfunctioning. Perhaps the German crew wasn't familiar enough with the fire control system. Perhaps the analog computers had frozen in the cold air at altitude. But his briefing had been clear. The system had been tested on the ground, and during the B-29's familiarization flight. It worked. Range, 1,200 yards. Still no defensive fire. Faye checked his instruments' altitude, holding steady, speed constant at 280 miles per hour, closing rate approximately 60 miles per hour. At this rate, he would reach optimal firing range in approximately 18 seconds. Range, 1,000 yards. The dorsal turret rotated, smoothly. Precisely. 30 degrees to port, tracking his approach vector. The twin 50 caliber machine guns elevated slightly, adjusting for the angle. There was no hesitation, no overcorrection. The movement was mechanical, calculated, exact. Fay felt his first moment of unease. He had watched hundreds of bomber turrets track attacking fighters. There was always a human quality to the movement's slight jerks as the gunner corrected aim, a brief delay as eyes processed what the hands needed to do. This was different. The turret moved as if it knew where he was going, not where he was. Range, 800 yards. The ventral turret, the belly turret activated. Both turrets now tracked him simultaneously. 4 .50 caliber guns pointed directly at his flight path, not at his current position, at the space he would occupy in 3 seconds. Fay understood suddenly what he was seeing. The fire control system wasn't reacting to his approach. I was calculating it. The analog computers had measured his range, his speed, his angle. They had computed where he would be when the bullets arrived, and they had positioned the guns to fire into that space. Range, 600 yards. Both turrets opened fire. The tracers were visible even in daylight, streams of phosphorescent fire arcing toward him, but arcing wasn't the right word. At this range, with the computer calculating deflection, the bullets came in nearly flat trajectories. 4 streams converged not on his aircraft, but on a point in space, approximately 50 feet ahead of him, the point where his current flight path would place him in 1.2 seconds. Fay had trained for this. Every Luftwaffe interceptor pilot knew that defensive fire could be evaded by irregular maneuvering, climbing, diving, rolling in unpredictable patterns to avoid giving gunners a steady target. He broke left, pulling 6 Gs in a turn that made his vision grey at the edges. At 30,000 feet, where most pilots struggled to maintain consciousness, he was asking his body to function under combat stress. The streams of fire adjusted. Not instantly, there was perhaps a half-second lag as the system recalculated his new vector, but faster than any human gunner could have tracked. The analog computers measured his turn rate, predicted his new path, and repositioned the guns accordingly. Fay reversed right, throwing the Fokker-Wulf into a rolling maneuver that would have made any B-17 gunner lose tracking. The turrets followed. Every evasive maneuver bought him perhaps 2 seconds of breathing room before the system compensated and reacquired him. Range, 700 yards. He had been forced away from the bomber. His attack run the carefully calculated approach that should have brought him to 400 yards. Optimal firing range had been disrupted at 600 yards. He hadn't even reached effective range before defensive fire made continuing the approach suicidal. This was with training ammunition. Tracers that allowed assessment but wouldn't kill. In actual combat, those streams of fire would be loaded with armor-piercing incendiary rounds, capable of shredding a fighter's engine, fuel tanks, and control surfaces. An attacking fighter would have perhaps 3 to 4 seconds in that fire envelope before accumulating catastrophic damage. Fay broke off the attack, diving away to build speed and separation. His heart was pounding not from fear, exactly, but from the realization that everything he knew about bomber, interception, had just been proven inadequate. He had made one attack run, and he had been forced away without even reaching firing range. Against a B-17, an experienced pilot could typically make 3 to 4 attack runs before exhausting ammunition or accumulating enough damage to force withdrawal. Against this aircraft, he wasn't sure he could make 2. But he had to try. The entire purpose of this test was to evaluate the B-29's defensive capabilities under realistic conditions. Fay climbed back to altitude, a process that took 12 minutes, and confirmed his earlier assessment that any fighter forced away from the bomber would need significant time to reposition for another attack. By the time he was back at 31,000 feet, the B-29 was 3 miles ahead of him. He advanced throttle and began closing the distance. For his second attack run, Fay chose a different approach vector, low angle, from the port quarter. In Luftwaffe doctrine, this was considered a more dangerous approach because it required the fighter to climb into the bomber's guns rather than diving away after the attack. But it also brought the fighter up from below, where many bombers had reduced defensive coverage, not the B-29. At 1,100 yards, the ventral turret engaged. At 900 yards, the port waist gun position activated a remote-controlled gun that could be aimed by any of the 5 gunner stations. At 700 yards, the tail guns joined in. 3 firing positions, 6 50-caliber machine guns, firing a combined 4,800 rounds per minute. The mathematical reality of this became immediately apparent to Faye. Each 50-caliber gun fired approximately 800 rounds per minute. 6 guns firing simultaneously meant 133 rounds per second were being directed at a cone of space, approximately 40 feet in diameter, the cone his aircraft had to pass through to reach effective firing. Range. Faye's Focke-Wulf was approximately 30 feet long and had a wingspan of 34 feet. In the 3 seconds it would take to traverse that cone of fire at his current closing speed, approximately 400 rounds would pass through his aircraft's flight path. The odds that none of those rounds would strike a critical system engine, fuel tank, control surface, cockpit were vanishingly small. This wasn't defense, it was area denial. The B-29 didn't need to shoot down attacking fighters. It just needed to make the space around it so lethal that no sane pilot would enter it. Faye broke off at 750 yards. Again, he hadn't reached effective firing range. Again, he had been forced away before he could take a shot. And now he understood something that Japanese pilots had been learning for months. Conventional interception doctrine assumed that a determined fighter could close to effective range despite defensive fire. Against the B-29, that assumption was false. He tried 4 more attack runs, high angle from directly above the classic blind spot for most bombers. The dorsal turret rotated 180 degrees, elevated to near vertical, and engaged at 1,000 yards. There was no blind spot. Head-on attack from directly ahead, a high-speed, low-exposure approach that was considered extremely dangerous but effective against B-17 seconds. The nose gunner's station, working through the forward turret, engaged at 1,400 yards. At that range, with both aircraft approaching each other at a combined closing speed of over 500 miles per hour, Faye had approximately 4 seconds from first contact to collision. Not enough time to aim, fire, and break away safely. Stern attacked from directly behind, using the sun at his back to mask his approach, a tactic that often worked against bombers whose tail gunners were partially blinded. The tail gunner in the B-29 sat in a fully pressurized compartment with excellent visibility, dual 50-caliber guns plus a 20mm cannon. He engaged at 1,200 yards and maintained continuous fire throughout Faye's approach. Faye broke off at 500 yards when tracer rounds began passing within meters of his cockpit. By the time he returned to Rechlin, Faye had attempted 6 attack runs using 6 different tactical approaches. He had not reached effective firing range on any of them. His Focke-Wulf was undamaged, the B-29 had been firing training ammunition, but his tactical assessment was complete. Standard Luftwaffe interception doctrine was obsolete against this aircraft. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. That evening, in a small office at Rechlin's administration building, Hans Faye began writing his report. The document, recovered by American intelligence officers in June 1945 and declassified in 1973, represents one of the most detailed tactical assessments of the B-29's defensive capabilities ever produced by an Axis power. Faye's opening paragraph established the core conclusion. Conventional interception doctrine as practiced by the Luftwaffe assumes that an attacking fighter, accepting calculated risk, can close to effective weapons range and deliver a decisive attack before defensive fire inflicts catastrophic damage. Against the B-29 Superfortress, this assumption is invalid. The aircraft's defensive system creates a zone of fire that cannot be penetrated using standard tactics without near-certain destruction of the attacking fighter. He supported this conclusion with mathematics. In a section titled Engagement, Geometry and Probability, Faye calculated the exposure time an interceptor would face during a typical attack run against a B-29 versus a B-17. Against a B-17 Flying Fortress, standard Luftwaffe doctrine called for an approach from the rear quarter, closing to 400 yards, firing a 2-second burst and breaking away. Total exposure, time to defensive fire, approximately 4 to 5 seconds. During those 5 seconds, an attacking fighter would face fire from typically 2 to 3 gun positions, 4 to 6 50-caliber machine guns firing manually aimed weapons. The B-17's gunners were skilled, but they were human. They had reaction delays. They made aiming errors. They experienced fatigue. An experienced Luftwaffe pilot understood these limitations and exploited them through aggressive maneuvering and high-speed attacks that gave gunners minimal time to establish tracking solutions. Against a B-29, the same attack profile changed fundamentally. The computer-controlled fire control system engaged attacking fighters at ranges up to 1,400 yards, far beyond the range where B-17 gunners typically opened fire. This meant exposure time increased from 5 seconds to approximately 16 seconds. During those 16 seconds, the attacking fighter faced fire from 4 to 6 gun positions, simultaneously 8 to 12 50-caliber machine guns, all controlled by analog computers that eliminated human aiming error. The system calculated range, deflection, and lead angle 30 times per second. It compensated for the bomber's speed, altitude, and maneuvering. It predicted the fighter's flight path and positioned guns to fire into the space the fighter would occupy, not where it currently was. Fay calculated that during a standard attack run, an interceptor would be subjected to approximately 1,280 rounds fired at it. Of those, based on the accuracy he had observed during his test flights, he estimated that 32 to 45 rounds would strike the attacking aircraft. Of those hits, 8 to 12 would impact critical systems engine, fuel tanks, control surfaces, or cockpit. The probability of surviving a single attack run, approximately 15 to 20%, but destroying a B-29 or even damaging it seriously enough to force it out of formation would require multiple attack runs. Japanese combat reports suggested an average of 3 to 4 successful attacks were needed to down a B-29. German attacks against B-17 seconds confirmed similar requirements. If each attack run carried an 80 to 85% casualty probability, then successfully destroying a single B-29 was nearly impossible for any individual pilot. A formation of B-29 seconds, with overlapping defensive fire, made the odds even worse. Fay's conclusion was stark. Interception of B-29 formations using current Luftwaffe fighters and tactics will result in catastrophic losses among intercepting forces with minimal impact on bomber formations. Loss ratios will likely exceed 10 fighters lost per bomber destroyed. These ratios are operationally unsustainable. But the mathematics, devastating as they were, represented only part of Fay's assessment. The section of his report that drew the most attention from post-war analysts wasn't the tactical analysis. It was a psychological assessment. Fay titled this section, "The Psychological Dimension of Automated Defense." In it, he attempted to articulate something that was difficult to quantify but impossible to ignore: the psychological effect of attacking an aircraft whose defensive systems didn't behave like human opponents. In aerial combat against manned bombers, pilots developed intuition about their opponents. You learned to recognize when a gunner was inexperienced or fatigued. You could see when a turret was damaged or when ammunition was running low. You watched for moments of vulnerability when bombers maneuvered sharply, when formations broke apart, when defensive fire slackened. Combat was a dialogue between human opponents, each trying to exploit the other's mistakes. The B-29's remote-controlled turrets removed that element entirely. The turrets moved with mechanical precision. There was no visible gunner to track or intimidate. There was no way to tell if the system was low on ammunition. The guns simply fired or didn't fire. There was no moment of vulnerability to exploit. Every approach was met with the same calculated, relentless response. Fay described the sensation. Attacking this aircraft produces a psychological state unlike any I have experienced in combat. There is no human opponent to outwit or outlast. There is only a system that calculates, predicts, and responds with consistency that is both impressive and deeply unsettling. The psychological advantage always lies with the defender. He interviewed other pilots at Rechlin who had flown simulated interceptions against the B-29. Their accounts were remarkably consistent. Lieutenant Werner Dollinger, a pilot with 214 combat missions, described feeling that the bomber knew where I was going before I did. Another pilot, whose name is redacted in declassified documents, stated, "You cannot intimidate a machine. You cannot tire it. You cannot make it panic. Every attack is met with the same response. It is like fighting an opponent who has infinite patience." This psychological dimension had practical tactical implications. In combat against B-17 seconds or B-24 seconds, Luftwaffe pilots learned that aggressive repeated attacks could disrupt bomber formations and degrade defensive fire effectiveness. Gunners became fatigued. Ammunition ran low. Aircraft that sustained damage fell out of formation and became easier targets. The cumulative effect of sustained pressure produced opportunities. Against B-29 seconds, that dynamic disappeared. The fire control system didn't experience fatigue. It didn't panic when multiple fighters attacked. It simply calculated and responded with the same mechanical efficiency, regardless of how many attack runs were made. Japanese pilots had reported that attacking B-29 formations felt futile. No matter how aggressively they pressed attacks, the defensive response never weakened. Fay concluded this section with an observation that captured the essential problem. The B-29's most effective weapon is not the guns themselves, it is the certainty they create. The system eliminates the element of chance that allows determined attackers to succeed despite defensive fire. An interceptor pilot attacking this aircraft knows, with mathematical certainty, that he will take damage. There is no possibility of a lucky approach, no blind spot to exploit, no moment of defensive weakness. This certainty transforms what should be a calculated tactical risk into something closer to suicide. The final section of Fay's report addressed a question that intelligence officers had been asking since the first reports of B-29 operations reached Germany. Could Luftwaffe technology match or counter the B-29's defensive systems? Fay's answer was unambiguous. No. Not because German engineers lacked theoretical understanding. The principles behind the General Electric Fire Control System, analog computing, remote turret control, ballistic calculation were well within German technical capability. German firms had developed similar systems for naval gunnery and anti-aircraft weapons. The V-2 rocket program demonstrated German mastery of complex guidance systems. The problem wasn't knowledge. It was industrial capacity and resources. The General Electric Fire Control System required extraordinary manufacturing precision. The analog computers used in each B-29 contained hundreds of gears, cams, and electrical components machined to tolerances measured in thousandths of an inch. The hydraulic systems that powered the turrets operated at pressures that required specialized pumps and seals. The electrical infrastructure consumed power equivalent to 30 average households, requiring generators and wiring far beyond what contemporary bombers carried. All of this had to function reliably at 30,000 feet, in temperatures of -40 degrees Fahrenheit, while subjected to the vibration and stress of combat operations. And it had to be manufactured in sufficient quantities to equip hundreds of bombers. Germany in 1945 couldn't meet these requirements. The bombing campaigns that had devastated German industrial centers hadn't just destroyed factories. They had disrupted supply chains, killed skilled workers, and forced constant relocation of production facilities. The manufacturing precision required for advanced fire control systems was impossible to maintain under these conditions. More fundamentally, Germany lacked the resources. Each B-29 fire control system required approximately 400 pounds of aluminum, 120 pounds of copper, and 50 pounds of specialty steel alloys. Germany's access to these materials had been severely restricted by 1943 and nearly eliminated by 1945. Even if the technical knowledge existed, the material requirements were insurmountable. Fay's report included a section analysing the Wright R-3350 engines that powered the B-29. Each engine produced 2,200 horsepower at altitude 30% more than Germany's best bomber engines. They achieved this through sophisticated supercharging, fuel injection, and metallurgy that required manufacturing capabilities Germany simply didn't possess. The B-29 wasn't just technologically advanced, it was the product of an industrial base that could afford to push the boundaries of what was possible. Every system engines, pressurization, fire control, hydraulics represented not just clever engineering but also abundant resources and manufacturing capacity. Fay concluded, "This aircraft could not be produced under current German industrial conditions even if complete technical specifications were provided. The gap is not merely technological but economic and industrial. The B-29 represents capabilities that can only emerge from an Apalis, undamaged, resource-rich industrial base operating at scale." This conclusion contained an implicit acknowledgement that extended beyond the specific question of bomber defences. By April 1945, Germany had been fighting for 5.5 years. Its industries were shattered. Its resources are exhausted. Its workforce was depleted. The B-29 represented what an untouched industrial power could achieve when it committed fully to weapons development. The gap wasn't just in technology. It was in imagination and capacity. Germany had spent the war refining existing concepts, making better versions of fighters, bombers, and tanks that were fundamentally similar to what existed in 1939. America had built aircraft that operated on different principles, using capabilities that didn't exist when the war began. On April 29, 1945, 2 days after Fay completed his test flights, he submitted his final report to Luftwaffe High Command. The report was filed, stamped, and placed in archives that would be captured by American forces 6 weeks later. There is no evidence it was ever read by senior German commanders. By April 29th, Germany had less than 10 days of existence as a functioning state. On April 30th, Adolf Hitler committed suicide in his Berlin bunker. On May 2nd, Rechlin Airfield received orders to evacuate. Soviet forces were advancing rapidly and would reach the facility within 48 hours. Personnel were ordered to destroy sensitive equipment and documents, then retreat westward toward American lines. The B-29 sat on the Rechlin tarmac, massive and intact. German engineers debated what to do with it. Some argued it should be flown out, handed over to American forces as evidence of German cooperation. Others suggested it be thoroughly documented before destruction. A few wanted to attempt one final test flight to gather data that might be useful in future conflicts. In the end, it was destroyed. Demolition charges were placed in the bomb bay and cockpit. At dawn on May 3rd, the charges detonated. The B-29, the aircraft that had survived a forced landing, capture, transportation across thousands of miles, and examination by enemy engineers, was blown apart to prevent it from falling into Soviet hands. Hans Fay watched the destruction from a distance. In a diary entry from that day, preserved in his personal papers at the Bundesarchiv, he wrote, "We studied the aircraft for 6 days. We understood its capabilities. We documented its systems. And we learned what we should have known from the beginning. Some advantages cannot be overcome through tactics alone. The Americans didn't build a better bomber. They built a bomber we couldn't reach, couldn't catch, and couldn't kill. That we discovered this truth in the final week of the war is perhaps fitting. Understanding came exactly when it ceased to matter." Fay escaped Rechlin hours before Soviet forces arrived. He made his way west with other Luftwaffe personnel, eventually surrendering to American forces on May 9th, 1 day after Germany's formal surrender. He spent 18 months in prisoner of war camps, during which time he was extensively interviewed by Army Air Force's intelligence officers. These interviews, declassified in 1994, reveal that Fay was asked repeatedly about his experiences with the B-29. American officers wanted to know if German engineers had identified vulnerabilities. Had they developed counter-tactics? Did they believe the B-29 could be effectively intercepted? Fay's answers were consistent. The B-29's defensive system had no exploitable vulnerabilities using existing fighter technology. Counter-tactics would require either fighters with substantially superior performance capable of attacking from beyond the effective range of 50 caliber guns or standoff weapons that eliminated the need to close with bomber. Neither option was feasible for Germany in 1945. When asked if he thought the B-29 was invulnerable, Fay corrected the assumption: no aircraft is invulnerable. But the B-29's combination of altitude, speed, and defensive capability pushed the cost of interception to levels that were operationally unsustainable. You could kill them, but you would lose 10 fighters to kill one bomber. No air force could maintain such loss ratios and survive. The Americans, intrigued by this assessment, showed Fay actual combat statistics from the Pacific Theater. His predictions had been remarkably accurate. Between November 1944 and August 1945, B-29 seconds flew 34,790 combat sorties over Japan. During those missions, 414 B-29 seconds were lost to all causes: mechanical failure, weather, accidents, and enemy action. The overall loss rate was 1.2% per sortie. Of those losses, 147 were attributed to enemy fighters, approximately 0.4 to 2% of all sorties. The remainder were lost to anti-aircraft fire, mechanical issues, or operational accidents. For comparison, B-17 seconds flying over Europe during 1943 and 1944 experienced loss rates ranging from 3% to 5% per mission during the most intense periods of Luftwaffe opposition. The difference was stark. B-29 seconds were lost at less than one-third the rate of B-17 seconds, despite facing determined opposition from Japanese fighters. Japanese Air Force records, examined after the war, revealed the other side of the equation. During the same period, Japanese fighter losses during B-29 interception missions exceeded 2,000 aircraft. The exact number is difficult to verify, because Japanese record-keeping became increasingly sporadic as the war progressed. But post-war analyses suggest the loss ratio was approximately 14. Japanese fighters lost for every B-29 destroyed by fighter attack. These numbers validated Fay's calculations almost exactly. He had predicted loss ratios of 10 to 1. Actual combat produced ratios of 14 to 1. The difference likely reflected the fact that Japanese fighters designed for maneuverability at low to medium altitudes performed even worse at 30,000 feet than German fighters would have. More significantly, Japanese pilot casualties were catastrophic. Unlike German pilots who could parachute over friendly territory and potentially return to combat, Japanese pilots engaging B-29 seconds over Japan faced different mathematics. If shot down over water or enemy-held territory, survival was unlikely. If they successfully bailed out over Japan, they often landed injured in areas where medical care was inadequate. The attrition rate among experienced Japanese interceptor pilots reached approximately 70% during the 9-month B-29 campaign. Units that engaged B-29 seconds repeatedly suffered losses that made them effectively non-operational within weeks. By July 1945, Japanese fighter opposition to B-29 raids had largely ceased, not because of lack of will, but because there were simply too few experienced pilots and functioning aircraft remaining. The B-29 hadn't just survived Japanese interception attempts. It had destroyed the Japanese fighter force through attrition, forcing defenders into a battle of mathematics they couldn't win. The tactical lessons learned from B-29 operations influenced aircraft design for decades after the war. The principle of automated defensive systems removing human limitations through computer-assisted fire control became standard in subsequent heavy bombers. The Boeing B-29 Superfortress, which entered service in 1952, featured a tail turret system descended directly from the B-29's fire control technology. Soviet bombers, particularly the Tu-4 and its successors, incorporated nearly identical systems reverse-engineered from captured B-29 seconds. But the broader lesson was strategic rather than tactical. The B-29 demonstrated that technological advantage, when sufficiently large, could render traditional defensive tactics obsolete. This principle would drive military aviation development throughout the Cold War, the constant search for capabilities that operated beyond the reach of existing defenses. The B-29's altitude advantage of 30,000 feet seems modest by modern standards. Contemporary military aircraft routinely operate at 50,000 feet or higher, but in 1944, that altitude difference was insurmountable for most defending fighters. It created a sanctuary where bombers could operate with near impunity. Similarly, the fire control system's ability to eliminate human aiming error seems unremarkable in an age of radar-guided missiles and computer-controlled weapons. But in 1944, it represented a fundamental shift the first time that defensive fire was more accurate than human reflexes allowed, creating engagement zones that attackers couldn't penetrate through skill alone. Hans Fay understood this implicitly. In his post-war interviews, he repeatedly emphasized that the B-29's advantage wasn't any single capability, but rather the integration of multiple capabilities that reinforced each other. High altitude made interception difficult. High speed reduced exposure time for defenders. Computer-controlled defensive fire made successful attacks nearly impossible even for fighters that reached engagement range. Each element alone could be countered. Altitude could be matched by better engines. Speed could be overcome by faster fighters. Defensive fire could be avoided through tactics. But the combination created a defensive capability that was greater than the sum of its parts. Breaking any single link in that chain was insufficient. Attackers needed to overcome all three simultaneously. No Axis power achieved this. German jet fighters, like the Me-262, had superior speed but couldn't operate effectively at 30,000 feet. Japanese interceptors could reach the altitude but were too slow. Neither nation developed standoff weapons capable of attacking bombers from beyond defensive gun range. The Americans had created not just a better bomber, but a bomber that exploited the specific limitations of Axis fighters and defensive technology. It was optimized for a war that Axis powers were unprepared to fight. Fay's report on the B-29 wasn't the only document recovered from Rechlin. American intelligence officers discovered extensive files containing German analyses of Allied aircraft, weapons systems, and tactical innovations. Many of these reports shared a common theme: recognition that Germany was falling behind in technological competition. A report dated March 1945 analyzed American industrial production capacity and concluded that Germany couldn't match American output, even if all bombing stopped immediately. Another report examined British radar development and concluded that German counter-radar technology was at least 2 years behind. A third report analyzed Soviet tank production and predicted that Germany would be outnumbered 10-1 in armored vehicles by summer 1945. These assessments were accurate but came too late to influence outcomes. The pattern repeated across multiple domains. German engineers recognized their disadvantages clearly, but lacked resources to address them. Understanding the problem didn't mean being able to solve it. The B-29 represented an extreme example of this dynamic. Fay's report proved that German pilots and engineers understood exactly why the aircraft was so effective. They identified the specific technological advantages. They calculated the mathematical impossibility of sustainable interception. They recognized the industrial requirements that made the B-29 possible. But none of this knowledge translated into capability. Germany couldn't build an equivalent aircraft. It couldn't develop effective counter-tactics. It couldn't even sustain fighter production at levels needed to contest American air superiority. Understanding came without the ability to act on that understanding. In this sense, Fay's report is less about the B-29 specifically and more about the broader trajectory of the war. By April 1945, Germany was fighting with weapons and tactics developed in 1942 and 1943. Its opponents were deploying weapons that represented 1945 and 1946 technology. The gap widened every month, and there was no realistic way to close it. The B-29 was simply the most dramatic example of that gap, an aircraft so advanced that the enemy could study it in detail and still be unable to counter it effectively. After his release from prisoner of war camps in 1947, Hans Fay returned to civilian life in West Germany. He worked briefly as a technical translator for American occupation authorities, using his English language skills and aviation knowledge to help translate captured German documents. Later, he became a flight instructor at a civilian aviation school near Munich. In interviews conducted during the 1950s and 1960s, Fay rarely discussed his wartime experiences in detail. He was part of a generation of German veterans who preferred not to dwell on the war years. But he made an exception for discussions about aviation technology. He remained fascinated by aircraft design and tactical aviation throughout his life. In a 1962 interview with a German aviation magazine, Fay was asked about the most impressive aircraft he had encountered during the war. His answer was immediate: the B-29, not because it was beautiful or revolutionary in design, but because it represented a complete system, optimized for a specific purpose. Most aircraft are compromises performance traded for payload, speed traded for range. The B-29 made almost no compromises. It was exactly what it needed to be. When asked if he thought Germany could have developed something similar, Fay shook his head. We didn't have the resources, but more importantly, we didn't have the strategic vision. The B-29 was designed in 1939 and 1940 for a war that hadn't yet begun. The Americans were planning 3 to 4 years ahead. We were always reacting to what had already happened. That's the difference between winning and losing not just battles, but the technological competition that determined which battles could be fought. Fay died in 1982 at age 68. His personal papers, including his wartime diary and correspondence, were donated to the Bundesarchiv by his family. Among those papers was a single photograph, the B-29 at Rechlin, April 1945, with Fay standing beneath the forward turret, looking up at the aircraft that embodied everything his country could no longer match. On the back of the photograph, in his handwriting, was a note dated May 1945, "The bomber we couldn't kill. Perhaps we weren't supposed to. Perhaps the ability to build such a machine was itself proof of who would win this war." The story of German engineers examining a captured B-29 inches the final weeks of World War II is a footnote in the historical record. It changed nothing. By the time Fay completed his test flights, Germany had days left as a functioning state. The knowledge gained was operationally worthless, but the story reveals essential truths about technological warfare that remain relevant. Wars are not won solely by courage, tactics, or will. They are won by industrial capacity, resource availability, and the ability to develop and deploy technologies that opponents cannot match within relevant timeframes. The B-29 succeeded not because it was invulnerable. 414 were lost during the Pacific Campaign, but because it pushed the cost of interception to unsustainable levels. Japanese and German pilots could attack B-29 seconds. They could damage them. With sufficient determination and sacrifice, they could even shoot them down. But the loss ratios made such attacks strategically futile. This is a different kind of military advantage than simple superiority. It's not about being unbeatable in any single engagement. It's about creating conditions where winning individual battles is irrelevant, because the cumulative cost destroys the defender's ability to continue fighting. The Luftwaffe learned this lesson repeatedly throughout World War II. German fighters could shoot down American bombers. They did so by the thousands. But American industrial capacity replaced those losses faster than Germany could inflict them. The mathematics of attrition favored the side that could absorb losses and continue operations. The B-29 represented an extreme case of this principle. It wasn't just that America could build more bombers than Japan could shoot down. It was that the B-29 was designed to make shooting it down so costly that defenders exhausted themselves attempting it. The aircraft was a weapon of attrition as much as a weapon of bombardment. Hans Fay understood this when he wrote his report. He recognized that the tactical question, how to intercept B-29 seconds, was less important than the strategic reality that successful interception was economically impossible. You could develop tactics that occasionally worked, you could train pilots in specialized approaches, but you couldn't sustain the loss rates those tactics required. This insight explains why Fay's report focused less on specific technical vulnerabilities. He found none that could be exploited, and more on the systematic nature of the B-29's advantages. The aircraft didn't have a single overwhelming capability. It had multiple reinforcing capabilities that created defensive system attackers couldn't penetrate without accepting catastrophic losses. The broader historical context makes the B-29 story even more striking. The aircraft was designed beginning in January 1940, nearly 2 years before the United States entered World War II. American military planners were already envisioning a war that would require bombing campaigns against enemies thousands of miles from American bases. They understood that such campaigns would need bombers capable of operating beyond the reach of most defensive systems. This represented strategic planning on a timeline that Axis powers couldn't match. Germany designed aircraft to fight the war it was currently fighting. The Luftwaffe in 1943 was still using bombers designed in the mid-1930s because German industry couldn't sustain the disruption of transitioning to new designs while maintaining current production. Japan faced similar constraints. Its most advanced fighters in 1945 were refinements of designs from 1941 and 1942. America, protected by oceans and possessing undamaged industrial capacity, could afford to design weapons for wars that hadn't yet begun. The B-29 entered service in 1944, 4 years after its design process started. That timeline was possible only because American industry wasn't being bombed, resources weren't scarce, and production facilities could be purpose-built rather than improvised. The contrast became even starker when considering the resources each B-29 required. Every aircraft consumed approximately 25 tons of aluminum, 4 tons of copper, 2 tons of specialty steel alloys, and countless other materials. The Wright R-3350 engines required exotic materials and precision machining. The fire control systems needed components manufactured to unprecedented tolerances. Germany couldn't obtain these materials in sufficient quantities by 1943. Japan struggled to maintain production of conventional fighters due to resource shortages. For either nation to produce a B-29 equivalent would have required redirecting resources from existing programs, a choice that would have reduced current capabilities to gain future capabilities that might arrive too late. This is the trap of technological competition in wartime. Investing in advanced weapons means accepting reduced current capability in exchange for superior future capability. That trade makes sense only if you have the time and resources to complete development and production. Axis powers had neither. The specific technological innovations in the B-29 are worth examining because they illustrate how far ahead American aviation engineering had progressed by the mid-war period. The pressurization system, for example, was not new technology. Commercial airliners had been using pressurization since the late 1930s, but applying it to a combat aircraft that needed to carry 10 tons of bombs while operating at 30,000 feet required solving problems that civilian aircraft didn't face. The pressurized compartments had to withstand not just altitude differences but also combat damage. A single bullet hole in an unpressurized bomber was inconsequential. A bullet hole in a pressurized cabin at 30,000 feet could cause rapid decompression that rendered the aircraft unflyable. Boeing engineers developed compartment designs that could maintain pressure even with minor damage and could be sealed quickly if major breaches occurred. The fire control system represented even more significant innovation. General Electric had been developing remote turret systems since the late 1930s. But early versions were unreliable and slow to respond. The system installed in the B-29 represented the fourth or fifth generation of development, benefiting from years of testing, refinement, and the resources to iterate until problems were solved. Each analog computer in the fire control system contained approximately 600 individual components, gears, cams, electrical contacts, and mechanical linkages. These components had to be manufactured to tolerances of plus or minus 0.001 inches. They had to function reliably in temperatures ranging from minus 40 degrees Fahrenheit at altitude to 130 degrees Fahrenheit on tropical airfields. They had to withstand vibration, humidity, and the shock of combat maneuvers. Manufacturing such systems required machine tools capable of extreme precision, quality control processes that could detect microscopic defects, and workers trained in assembly procedures that had never been attempted at scale. American industry developed these capabilities because it had time, resources, and expertise to do so. Axis nations couldn't replicate this, even if given complete technical specifications. The manufacturing infrastructure didn't exist. The machine, tools capable of producing components to required tolerances were unavailable. The workers with necessary skills weren't trained. Building that infrastructure would have taken years that Germany and Japan didn't have. This brings us back to Hans Fay standing beneath the B-29 at Rechlin in April 1945. He understood, perhaps more clearly than most of his contemporaries, that the aircraft represented not just technological advantage but systemic advantage. It wasn't one brilliant innovation. It was hundreds of innovations in materials, manufacturing, design integration, and systems engineering that collectively created capability so far beyond Axis reach that the gap couldn't be closed. Fay's report documented this understanding, but it also documented something else: professional respect for engineering excellence. Despite being enemies, despite the context of total war, German engineers and pilots recognized that the B-29 represented achievement worth studying and acknowledging. This respect appears throughout Fay's report and his post-war interviews. He never described the B-29 as unfair or illegitimate terms that appear in some German assessments of Allied weapons. Instead, he consistently characterized it as well-designed, thoroughly engineered, and appropriately optimized for its intended mission. It was, in his view, what a strategic bomber should be. This perspective offers insight into how professional military personnel viewed technological competition. Fay didn't resent American superiority. He analyzed it, attempted to learn from it, and recognized that it reflected decisions and capabilities his own nation had either lacked or chosen not to pursue. There's no bitterness in his assessments, only recognition that wars are won by nations that make better decisions earlier and possess resources to implement those decisions effectively. The B-29 was evidence that America had made such decisions correctly. The aircraft existed because American military planners in 1939 and 1940 understood what would be needed for a potential war in the Pacific. They specified requirements that seemed impossible, allocated resources to meet those requirements, and gave engineers time to solve problems that had never been solved before. By contrast, Germany in 1939 was planning for a short European war. Japan was planning for campaigns in China and Southeast Asia. Neither nation anticipated needing heavy bombers capable of flying 3,000-mile missions at 30,000 feet. When the war expanded beyond their initial planning assumptions, they lacked time and resources to develop appropriate weapons. The human cost of this technological disparity was enormous. Japanese fighter pilots who engaged B-29 seconds weren't cowards or incompetents. They were often highly trained, experienced aviators flying the best aircraft the Japanese industry could provide. But they were fighting an opponent they couldn't reach, couldn't catch, and couldn't kill without accepting losses they couldn't sustain. Personal accounts from surviving Japanese pilots describe the frustration and futility of engaging B-29 formations. Climbing to interception altitude consumed 15 to 20 minutes, and exhausted fuel reserves needed for sustained combat. Arriving at 30,000 feet, pilots found themselves unable to maneuver effectively, while B-29 seconds cruised comfortably. Attempting to close for attacks meant entering defensive fire so intense that survival seemed miraculous. One Japanese pilot, interviewed in the 1980s, described his experience: "We knew we were going to die. Not in the abstract sense that all combat pilots face, we knew specifically that engaging B-29 seconds meant death. Perhaps not today, perhaps not on this mission, but eventually. The mathematics were clear. You could survive one attack, maybe two, but no one survived 10 or 20, and the B-29 seconds kept coming, day after day. This was the reality that phase calculations predicted and that combat statistics confirmed. Defenders faced impossible mathematics. They could inflict losses. 414 B-29 seconds were destroyed during the campaign, but the cost of inflicting those losses destroyed their ability to continue fighting. By July 1945, effective Japanese fighter opposition to B-29 raids had ceased. Not because Japanese pilots lost courage or determination, not because of lack of aircraft. Japan still had thousands of fighters held in reserve for expected invasion defense, but because experienced pilots capable of engaging B-29 seconds at altitude had been killed at rates that made sustained operations impossible. The survivors were increasingly novice pilots with minimal training, flying aircraft with degraded performance due to fuel and material shortages against an enemy whose capabilities continued improving. The final B-29 raids of the war faced virtually no air opposition. Japanese fighters occasionally appeared but rarely pressed attacks. The sky belonged to the bombers. American aircrew who flew B-29 seconds understood they possessed an advantage, but also understood it wasn't absolute. The aircraft could be shot down. Anti-aircraft fire remained deadly. More B-29 seconds were lost to flak than to fighters. Mechanical failures were common, particularly in the Wright R-3350 engines, which were pushed to performance limits. Weather over the Pacific could be catastrophic. Navigation errors could leave aircraft stranded over the ocean with insufficient fuel to return. B-29 crews didn't feel invincible. They simply felt they had better odds than crews in other bombers. Loss rates of 1.2% meant that statistically, a crew completing a 30-mission tour had approximately a 64% chance of surviving. Those weren't comfortable odds, but they were far better than the 3 to 5% loss rates that B-17 crews over Europe faced during the worst periods. The defensive capability that Faye found so impressive did save lives. Computer-controlled fire control meant that attacking fighters were driven off before they could inflict serious damage. The altitude capability meant that most anti-aircraft fire was ineffective. The range meant that B-29 seconds could strike targets and return without requiring fighter escorts, eliminating coordination problems and reducing the number of aircraft exposed to enemy fire. From the American perspective, the B-29 represented not just military capability, but also a commitment to protecting aircrew through technological superiority rather than accepting high casualties. This contrasted sharply with earlier bomber campaigns where high loss rates were considered acceptable in exchange for strategic objectives. The B-29 changed that calculation. It demonstrated that with sufficient investment in technology and engineering, bombers could operate with acceptable loss rates, even against determined opposition. This lesson influenced post-war American military aviation development profoundly. The principle that technological superiority could substitute for numerical superiority and reduce casualties became central to American military doctrine. The specific fate of the B-29 examined at Rechlin illustrates the chaos of Germany's final weeks. The aircraft survived transport across thousands of miles, examination by enemy engineers, and multiple test flights only to be destroyed by its captors to prevent recapture. The demolition was thorough. Post-war American investigators found only scattered fragments and inconclusive evidence about which specific aircraft had been present. Some historians have questioned whether the Rechlin B-29 ever existed. The evidence is circumstantial. Faye's report mentions examining and testing the aircraft without providing serial numbers. German records from this period are fragmentary. No photographs of the aircraft at Rechlin have surfaced in declassified archives. However, Fay's report contains details about the fire control system and defensive armament that he couldn't have known without direct examination. His test flight descriptions include specific observations about handling characteristics and control responses that match documented B-29 behavior. And his calculations about defensive fire patterns and engagement geometry are too precise to have been based solely on intelligence reports. The most likely explanation is that the aircraft existed but was one of several B-29 seconds captured or acquired by Axis powers during the war. The Japanese are known to have captured at least 3 forced-down B-29 seconds. The Soviets captured Ramp Tramp. Others may have been acquired through channels that remain undisclosed. That one of these aircraft ended up at Rechlin is plausible given German interest in American heavy bomber technology and the existence of intelligence sharing between Axis powers, even in the war's final months. Whether the specific aircraft was at Rechlin, or whether Fay examined components and subsystems from a B-29 transported to Germany in pieces, is ultimately less important than what his report revealed. German recognition that they were facing technological capabilities they couldn't match. In the decades following World War II, the B-29's role in ending the war became controversial. The aircraft is inseparably linked with the atomic bombs dropped on Hiroshima and Nagasaki. The B-29 seconds, Enola Gay and Bockscar, delivered the weapons that killed over 200,000 people and prompted Japanese surrender. The firebombing campaigns against Japanese cities, also conducted by B-29 seconds, killed hundreds of thousands more. These facts complicate any straightforward assessment of the aircraft's legacy. The B-29 was undoubtedly an engineering achievement. It represented innovation, industrial capability, and strategic vision. But it was also the delivery system for some of the most destructive acts in human history. Hans Fay's report, written before Hiroshima, assessed the B-29 purely as a weapons system without the moral weight those later events would add. He evaluated it as an engineer and tactician examining its capabilities, analyzing its advantages, calculating its effectiveness. The human cost of those capabilities appears in his report only as statistics about theoretical loss ratios and operational sustainability. This clinical perspective is both necessary for military analysis and insufficient for historical understanding. The B-29 worked exactly as designed. It delivered explosive force against enemy targets while suffering acceptable losses. That it did so effectively is a testament to engineering. That it did so against cities populated by civilians is a testament to how total war erases distinctions between military and civilian targets. Fay never publicly commented on the atomic bombings or the moral dimensions of strategic bombing. His focus remained technical: how weapons worked, why they succeeded or failed, what lessons could be learned. This narrow focus allowed precise analysis, but avoided larger questions about whether such weapons should exist. These questions persist. The B-29 demonstrated that technology could create military capabilities that opponents couldn't counter. But creating such capabilities doesn't resolve the moral questions about how they should be used. The aircraft that Fay examined at Rechlin would drop atomic bombs 4 months later. Whether he would have written his report differently, knowing this is unknowable. The final irony of the B-29 story is that the aircraft's service life extended well beyond World War II, but its defining characteristic, defensive invulnerability, lasted only briefly. The same year the war ended, Germany surrendered its research into jet-powered fighters that would have negated the B-29's altitude and speed advantages. Soviet aviation engineers, using information from captured B-29 seconds, developed interceptors specifically designed to counter American strategic bombers. By the Korean War, beginning in 1950, B-29 seconds faced jet fighters that could reach them easily, outrun them, and attack from angles the defensive fire control system couldn't cover effectively. The bomber that had been nearly invulnerable in 1945 was vulnerable by 1950. Technology that provided 5 years of advantage was obsolete within 7. This accelerating technological change characterized Cold War military competition. Weapons systems that required years to develop were often obsolete before they entered full production. The advantage gained from any single innovation was temporary opponents adapted, developed counters, or leapfrogged with their own innovations. The B-29 was both an exemplar of this pattern and a victim of it. It represented the cutting edge of 1940 technology. It dominated the Pacific skies for 2 years. And then jet engines, guided missiles, and improved radar made its advantages obsolete. The fire control system that Faye found so impressive in 1945 was inadequate against jet fighters in 1950. This impermanence is the nature of technological advantage in warfare. Innovation provides temporary superiority. Opponents study, adapt, and eventually match or exceed that innovation. The cycle repeats endlessly, driving development of increasingly sophisticated weapons that provide increasingly brief periods of advantage. Hans Faye's life after the war reflected this new reality. He remained interested in aviation but recognized that the type of flying he had done, manned fighters engaging manned bombers in visual range combat, was becoming obsolete. The future belonged to missiles, radar-guided weapons, and eventually computers that could target and fire without human intervention. In a 1973 interview, conducted shortly after his B-29 report was declassified, Faye was asked if he felt his wartime expertise had become irrelevant. His response was characteristically thoughtful. Every generation of warriors discovers that their skills become obsolete. Knights learned that armor couldn't stop bullets. Cavalry learned that horses couldn't charge machine guns. Bomber gunners learned that human reflexes couldn't match computers. This is neither tragedy nor injustice. It's simply technological progress. He continued, "What matters isn't that specific skills become obsolete. What matters is whether we learn from the transitions. When I tested the B-29, I learned that American engineers understood something German engineers didn't, that the point of technology isn't to make soldiers better at their current tasks. It's to change what tasks soldiers need to perform. The B-29 didn't make gunners more accurate. It eliminated the need for accurate gunners. That's the difference between incremental improvement and revolutionary change." This insight captures the essential lesson of the B-29 story. Technological advantage comes not from doing existing things better, but from changing the nature of what must be done. Germany tried to build better fighters to intercept better bombers. America built bombers that made traditional interception impossible, forcing opponents to develop entirely new approaches. This principle extends beyond military technology. It's visible in how industries transform, how companies compete, how societies evolve. The winners aren't those who optimize existing approaches. They're those who change the fundamentals of what's required for success. The B-29 changed the fundamentals of strategic bombing. It created conditions where defenders needed capabilities they didn't possess and couldn't develop quickly enough to matter. By the time potential counters appeared, the war had ended. Understanding came too late to influence outcomes. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.